Tropical meteorologists have pointed out that rapid intensification events have nearly doubled in frequency over the last 4 decades across the Atlantic and Pacific basins. Coastal infrastructure designed to withstand gradual wind increases is simply unprepared for storms that gain 50 to 70 miles per hour of wind speed in a single afternoon. It represents a fundamental shift in how coastal disasters unfold. If a major storm can jump 3 intensity categories in a single night, how prepared do you think our coastal cities really are? Type your thoughts in the comment section below, and if you're finding this breakdown valuable, take a quick second to subscribe and join our community of science explorers. While the oceans are storing unprecedented amounts of energy, another silent danger is building high above the clouds in the stratosphere. Every winter, a swirling vortex of freezing air forms tens of thousands of feet over the North Pole, known as the stratospheric polar vortex. When this vortex is strong and circular, it acts like a tight spinning top that keeps the coldest air on Earth locked directly over the Arctic ice cap. Traditionally, forecasters expected this polar vortex to stay stable throughout most of the winter season. They treated polar outbreaks as rare, once-in-a-decade events that only happened when an extraordinary weather system bumped into the Arctic Circle. The polar vortex was seen as a reliable shield that protected the heavily populated cities of North America, Europe, and Asia from true Arctic freezes. Yet atmospheric data reveals that the polar vortex is breaking down and splitting apart much more frequently than in the past. This breakdown happens through a wild event called Sudden Stratospheric Warming. In just a few days, temperatures 50,000 feet above the North Pole can jump by as much as 70 degrees Fahrenheit. That massive burst of heat rips the spinning polar vortex into 2 or 3 separate pieces. When the polar vortex splits, those pieces do not stay at the North Pole. They drift southward, carrying chunks of pure Arctic air directly over major population centers. In February of 2021, a fractured piece of the polar vortex plunged all the way down into Texas, a region famous for mild winters and warm sunshine. Temperatures plummeted below zero, freezing natural gas pipelines, knocking out the electric power grid for millions of people and causing billions of dollars in damage. What surprised power grid operators the most was how rapidly the freeze overwhelmed modern infrastructure. Water pipes burst inside millions of homes. Roads became impassable sheets of black ice, and hospitals were forced to operate on emergency generators in sub-freezing temperatures. It showed that our modern high-tech society is surprisingly fragile when extreme weather steps outside historical boundaries. A similar breakdown occurred in East Asia, where polar air broke through atmospheric boundaries and swept into southern China and Japan. Subtropical regions that rarely ever see snow experienced freezing rain, ice-covered highways, and widespread agricultural failure. These sudden cold snaps prove that a warming planet does not mean winter disappears. Instead, it means winter becomes erratic, unpredictable, and capable of striking regions that have zero defenses against extreme cold. These deep freezes also wreak havoc on municipal water systems that were never engineered for prolonged sub-zero temperatures. In southern cities, water mains are buried only a few inches below the ground surface because the soil rarely freezes. When a polar vortex split pushes frost lines several feet into the dirt, thousands of underground pipes crack simultaneously, cutting off running water to hundreds of thousands of residents for weeks. This brings us to another critical concept that scientists are watching closely: the phenomenon of compound weather events. In the past, meteorologists analyzed weather threats in isolation. They studied heat waves on their own, droughts on their own, and floods on their own. They assumed that a region might face one bad event, recover, and then deal with the next event several years down the road. However, the new reality of atmospheric shifts involves multiple disasters hitting the exact same region simultaneously or in rapid succession. For example, an intense heat wave dries out vegetation and soil, turning forests into giant tinderboxes. A few weeks later, a dry lightning storm ignites massive wildfires across millions of acres. Then, before the land can even begin to heal, a torrential atmospheric river dumps feet of rain on the burned hillsides, triggering catastrophic mudslides that sweep away entire neighborhoods. We are seeing this compound disaster cycle repeat across California, Greece, Australia, and Canada with disturbing frequency. When soil is severely burned by wildfire, it develops a hard, waxy crust that cannot absorb water. Even normal rainfall cannot penetrate the ground, turning what should have been helpful rain into destructive flash floods that wash away highways and bridges. Atmospheric rivers are another piece of this shifting puzzle that are growing in both size and strength. These are long, narrow bands of concentrated water vapor in the sky that carry as much water as the mouth of the Mississippi River. When an atmospheric river hits a mountain range, it is forced upward, dumping astonishing amounts of rain and snow in a very short window of time. In 2023 and 2024, a relentless train of atmospheric rivers battered the west coast of North America. Storm after storm slammed into the coast, refilling reservoirs that had been empty for a decade, but also causing widespread flooding and destabilizing steep hillsides. The sheer volume of water falling from the sky broke records that had stood for more than a century. What makes atmospheric rivers especially dangerous is their ability to trigger rain-on-snow events in high mountain passes. When a warm atmospheric river sweeps over a heavy mountain snowpack, it does not add fresh powder. Instead, the warm tropical rain melts the existing snow in hours, doubling the volume of runoff rushing down into river valleys below and overwhelming dams and levees. Hydrologists estimate that a single strong atmospheric river event can transport more than 20 times the average flow rate of the Mississippi River across the sky. When several of these rivers stall overpopulated river basins, emergency spillways on major hydroelectric dams must be opened at maximum capacity to prevent catastrophic structural failures, inundating downstream agricultural land. Do you think our current flood barriers and electrical grids can handle back-to-back megastorms? Share your perspective in the comments, and do not forget to hit subscribe so you never miss our deep dives into the powerful forces shaping our world. As we look at all these puzzle pieces together, a striking pattern begins to emerge. The Atlantic Ocean conveyor belt is slowing down, the jet stream is developing extreme kinks, the tropical Pacific is swinging with violent intensity, the polar vortex is fracturing, and atmospheric rivers are dumping unprecedented volumes of water. None of these events are happening in a vacuum. They are all interconnected gears in a single, massive global machine. To understand how interconnected this system truly is, scientists look at teleconnections. A teleconnection is a scientific term for how a weather event in one corner of the globe can trigger a completely different weather event thousands of miles away. For example, when warm ocean water builds up in the Indian Ocean, it changes thunderstorm patterns that alter the high-altitude winds over the Pacific. Those winds then bend the jet stream over North America, which ultimately decides whether someone in Chicago gets a snowstorm or a warm, sunny afternoon. This interconnectedness means that a shift in one part of the world can set off a chain reaction across continents. When the Sahara Desert experiences an unusual surge of moisture, it can suppress hurricane formation in the Atlantic for a few weeks, while simultaneously shifting rainfall belts into southern Europe. Everything on Earth is linked by a delicate web of physics, pressure, and temperature. Consider what happens when massive wildfires in the boreal forests of Siberia and Canada pump millions of tons of black soot into the upper atmosphere. That dark soot travels on high-altitude winds across the Arctic Ocean, eventually settling on top of pristine snowfields in Greenland and northern Scandinavia. Because dark surfaces absorb sunlight rather than reflecting it, that soot accelerates the melting of ice sheets miles away from the original fires. This runoff then feeds freshwater directly into the North Atlantic, further destabilizing the AMOC ocean conveyor belt. In this way, a forest fire in North America directly influences ocean currents that regulate winter temperatures in Great Britain and Scandinavia. It is a stunning example of how localized atmospheric disruptions can cascade across thousands of miles of ocean and air. Furthermore, changes in the Indian Ocean dipole, a temperature swing between the eastern and western halves of the Indian Ocean, can dramatically alter monsoon seasons in South Asia. When the western Indian Ocean becomes unusually warm, countries like Pakistan and India can experience extreme monsoon seasons that flood millions of acres of farmland, destroying global staple crops like rice and cotton. Right now, meteorologists are closely monitoring deep ocean temperature anomalies in the southern hemisphere. The Southern Ocean, which surrounds the frozen continent of Antarctica, has long been considered the greatest heat sink on the planet. Its cold, churning waters absorb enormous amounts of excess energy and carbon from the atmosphere, acting as a giant thermal buffer for the rest of the world. However, satellite observations in recent years show that Antarctic sea ice has dropped to historic, unprecedented lows. For decades, Antarctic sea ice had remained relatively stable, even expanding slightly in certain regions, but suddenly, millions of square miles of sea ice failed to form during the polar winter, leaving dark ocean water exposed to the sky. When white ice is replaced by dark water, a dramatic change in physics takes place. White ice acts like a giant mirror, reflecting up to 80% of incoming sunlight back into space. Dark ocean water does the exact opposite, absorbing over 90% of that solar energy as heat. This creates a powerful feedback loop. Warmer water prevents ice from forming, and the lack of ice causes the water to absorb even more heat. As the Southern Ocean warms, it begins to alter the circumpolar current, the strongest ocean current on Earth that flows endlessly around Antarctica. If this current weakens or shifts southward, it allows warmer water to lap against the base of massive Antarctic glaciers like the Thwaites Glacier, often called the Doomsday Glacier. Melting these massive ice sheets from beneath accelerates sea level rise across every continent on the planet. Glaciologists using underwater robotic submarines have already mapped deep channels carved into the underside of these Antarctic ice shelves by warm ocean currents. These channels allow warm water to reach the grounding line, the critical anchor point, where the glacier rests on the solid bedrock below sea level. If these grounding lines retreat inland, huge sections of the ice sheet could slip into the sea, fundamentally redrawing coastal maps across the globe. This brings us to the ultimate question that scientists around the world are racing to answer. Are we witnessing temporary extreme anomalies, or has Earth crossed into a fundamentally new weather regime? If our climate has shifted into a new regime, the historical weather records that engineers used to build dams, bridges, homes, and power plants may no longer apply. For over a century, civil engineers designed city drainage systems based on what they called the 100-year flood. This was a statistical calculation of the biggest storm a city could expect to see once in a century. Today, cities across the world are experiencing supposed 100-year floods every 3 to 5 years. The old statistical maps are becoming obsolete, and the cost of rebuilding damaged infrastructure is skyrocketing into the hundreds of billions of dollars. When cities are hit by rainfall that exceeds their drainage capacity by 300%, water backs up into subway tunnels, floods underground electrical substations, and turns urban streets into fast-flowing rivers. Engineers are realizing that designing infrastructure based on past 20th century weather records is like driving a car while looking only in the rearview mirror. This shift is not just an abstract scientific concept discussed in university lecture halls. It touches every single aspect of our daily lives. It affects the price of the food you buy at the grocery store, the cost of heating and cooling your home, the price of home insurance, and the safety of the community where your family lives. When crop yields drop in South America due to an unexpected drought, the global price of grain and cooking oil rises for families thousands of miles away. When a hurricane knocks out oil refineries along the Gulf of Mexico, fuel prices jump across entire continents. We live in a tightly connected global society where localized weather disasters instantly create global economic ripples. Insurance companies are among the first major industries to feel the financial shock of this shifting reality. In several coastal and wildfire-prone regions, major insurance providers have completely stopped writing new homeowner policies. They have calculated that the frequency and severity of extreme weather events make insuring homes in these areas economically impossible under traditional business models. When insurance companies leave a market, ordinary homeowners find it nearly impossible to secure mortgages or sell their properties, triggering sudden real estate drops in vulnerable regions. Local governments also lose property tax revenue, making it even harder for towns to finance the seawalls, storm drains, and backup generators needed to protect their citizens. What makes this moment in history so unique is that humanity now possesses the scientific tools to monitor these massive shifts in real time. We have thousands of satellites orbiting the planet, autonomous robot floats diving through every ocean basin, and supercomputers running trillions of calculations every second. We are no longer blind to the inner workings of our atmosphere. Yet having the data and truly understanding what it means for our future are two very different things. The challenge of the coming decades will be adapting our cities, our farming systems, and our emergency plans to a world where the weather no longer plays by the old rules. It means building resilient power grids that can survive deep freezes, designing cities that can absorb sudden megafloods, and developing crops that can thrive in erratic growing seasons. Every single shift we are seeing in the ocean and atmosphere reminds us of one fundamental truth. Earth is not a static rock floating in space. It is a living, breathing, dynamic system driven by immense physical forces that dwarf human engineering. Understanding these forces is the first and most critical step in preparing for whatever comes next. The atmosphere is constantly giving us clues about what lies ahead, and those who pay attention to the real science will be the ones best prepared for the unexpected turns of our changing world. If you found this deep dive into Earth hidden weather systems eye-opening, please take a moment to subscribe to the channel and turn on the notification bell so you never miss our upcoming science stories. We would love to hear your thoughts. Which of these weather shifts do you think poses the biggest challenge for our future? Drop your answer in the comments below and share this video with a friend or family member who loves exploring the mysteries of our planet. Thank you so much for spending your time with us today, and we look forward to seeing you in the next one. Deep beneath the calm blue waters of the North Atlantic Ocean, a giant invisible river of heavy salt water is quietly losing its momentum. Nobody can see it from the surface, and ships sail right over it without noticing a single thing. Yet instruments placed miles under the waves are picking up a pattern that has not occurred in over 1,000 years. A massive global engine in our atmosphere is shifting gears, and almost nobody is ready for what comes next. If you enjoy uncovering the real science behind our changing planet without any hype or exaggeration, make sure to hit that subscribe button right now. We track the strangest shifts in Earth and space, so you always stay one step ahead of the curve. To understand why this quiet shift has scientists watching their computer screens with genuine concern, we have to travel back in time for just a moment. For thousands of years, human civilization has enjoyed what experts call a sweet spot of steady weather. Our ancestors planted crops in the spring, harvested in the autumn, and knew roughly how cold the winter would be. We built entire cities right along coastlines and river valleys because the ocean currents followed a dependable, predictable routine. That routine was powered by something called the Atlantic Meridional Overturning Circulation, or AMOC for short. Think of the AMOC as a massive conveyor belt running through the world ocean. It takes warm water from the equator, carries it all the way up toward Europe and North America, and releases heat into the air like an enormous radiator. When that warm water cools off near the Arctic, it becomes heavier and saltier, sinking thousands of feet down to the seafloor. Then it slowly creeps back south along the bottom of the world to start the whole journey all over again. For decades, textbook science told us this ocean conveyor belt was virtually unstoppable. Generations of climate researchers believed the Atlantic current was far too massive to ever slow down in our lifetimes. They assumed it was like a freight train loaded with millions of tons of steel that would keep rolling forward on its tracks for centuries. The math models suggested that any major slowdown was something that belonged strictly to a distant future, thousands of years away. However, when marine scientists actually dropped deep-sea sensors across the ocean between Florida and the Canary Islands in the early 2000s, they found something very different. The ocean conveyor belt was not running at full speed. In fact, measurements collected by international ocean research teams showed that the entire system has slowed down by roughly 15% since the middle of the 20th century. That 15% drop might sound like a small number on paper, but in ocean terms, it equals the force of dozens of Amazon rivers suddenly vanishing from the global circulation system. This sudden change matters because ocean currents do not just move water. They dictate where rainfall lands, how intense storms become, and how cold our winters get on land. When an ocean current carries less heat northward, the energy in the system does not simply disappear. Instead, that heat gets trapped in the tropics and the southern seas, while the northern parts of the globe experience strange, disjointed weather patterns that catch communities completely off guard. Before we look at the next part of this mystery, it helps to understand what happens when fresh water gets dumped into salty water. Most people know that salt water is heavier and denser than plain tap water. In the freezing waters around Greenland, that extra weight from salt is the exact reason water sinks into the deep abyss to pull the conveyor belt forward. If the water does not sink, the belt stops pulling and the entire cycle begins to stall out. In recent years, giant ice sheets across Greenland and the Arctic have been melting much faster than early models predicted. That runoff sends trillions of gallons of pure, fresh meltwater pouring directly into the North Atlantic Ocean. Because fresh water is light and does not want to sink, it sits on top of the salty water like a layer of oil over vinegar. This forms an enormous cap of fresh water that blocks the sinking process entirely, jamming the gears of the world ocean engine. Scientists at Utrecht University in the Netherlands recently ran an advanced computer simulation to see what a tipping point would actually look like in real life. For months, their supercomputers crunched complex physics equations to track how the ocean responds to this freshwater buildup. What they discovered shocked the meteorological community. The ocean conveyor belt does not just slow down gradually in a smooth line. Instead, it reaches a hidden threshold where it can suddenly collapse in a matter of decades. Oceanographers studying deep sediment cores from the North Atlantic seabed have confirmed that similar rapid shutdowns happened during the last ice age. When the conveyor belt collapsed back then, winter temperatures across parts of Western Europe plummeted by more than 10 degrees in less than 20 years. It proves that sudden, sharp climate shifts are not just theoretical ideas in a computer model, but real events written permanently into Earth geological history. Did you realize that an invisible current in the middle of the ocean could control the weather right outside your front window? Drop a quick comment below with your guess on whether ocean shifts happen faster than air shifts, and tap that like button if you want more deep dives into hidden Earth systems. When that tipping point arrives, the consequences will not look like a smooth, gentle rise in temperature. Instead, it triggers a wild seesaw effect across the entire globe. In places like Northern Europe, including the United Kingdom, Norway, and Germany, winters could suddenly turn brutally cold, dropping average temperatures by 10 to 20 degrees within a short generation. Meanwhile, the southern hemisphere and the tropical zones would face intense heat waves and violent monsoons because the heat has nowhere to escape. To understand why this is so dangerous, we have to look at how modern society is built. We grow our wheat, corn, and soy in specific agricultural belts that rely on steady rain and predictable frost dates. If the growing season in Europe or North America shrinks by even 3 or 4 weeks, crop yields drop dramatically. Farmers who have followed the same seasonal calendar for generations suddenly find that the ground is too frozen to plant in April or too flooded to harvest in September. This brings us to the second major weather shift that is unfolding right above our heads in the upper atmosphere. High up in the sky, about 6 to 10 miles above the ground, flows a fast-moving river of air known as the jet stream. Under normal conditions, the jet stream acts like a tight rubber band that loops around the northern part of the planet. It keeps the freezing polar air locked safely at the North Pole while keeping milder air down where most people live. For a very long time, meteorologists believed the jet stream was steady enough to act as a permanent barrier between the Arctic and the mid-latitudes. They treated the jet stream like a reliable boundary line on a weather map that only moved slightly north in the summer and slightly south in the winter. Weather forecasts across the world relied on this assumption to predict seasonal storm tracks weeks in advance. Yet, over the past few years, pilots and atmospheric scientists have observed the jet stream doing something completely abnormal. Instead of blowing in a tight, fast circle around the planet, the jet stream has become wavy and sluggish, like a lazy river looping back and forth across continents. When the jet stream gets these massive giant kinks in it, weather systems get completely stuck in place for weeks at a time. Meteorologists call this phenomenon atmospheric blocking. When a high-pressure system gets trapped inside one of these giant jet stream loops, it acts like a giant boulder in a creek. Cool ocean breezes cannot push past it, and rain clouds are forced to go completely around it. Underneath that stuck high-pressure dome, the air compresses, heats up, and bakes the landscape beneath it day after day without any relief. This is the exact mechanism that triggered the historic Pacific Northwest heat dome in the summer of 2021. Towns in British Columbia, Canada, reached scorching temperatures of 121 degrees Fahrenheit. That is roughly 49 degrees Celsius, a level of heat more common in Death Valley than in a coastal rainforest filled with pine trees. Roads buckled, power cables melted, and marine life literally cooked inside their shells along the shoreline because the weather simply refused to move. On the other side of that same wavy jet stream loop, the opposite disaster occurs. When a deep, low-pressure trough gets stuck in place, storm after storm tracks over the exact same piece of land. Instead of rain falling for an afternoon and moving on, torrential rain pours down for days without stopping. This was the driving force behind catastrophic flooding events in Central Europe, where river basins received months' worth of rainfall in less than 48 hours, wiping away historic villages and infrastructure. What makes this wavy jet stream so alarming is what scientists call the Arctic amplification effect. Because the Arctic is warming nearly 4 times faster than the rest of the planet, the temperature difference between the North Pole and the equator is shrinking. The jet stream gets its speed and power strictly from that temperature contrast. When the contrast gets smaller, the jet stream loses its strength, becoming floppy and prone to extreme stalling events. To make matters even more complicated, this atmospheric stagnation affects how cities breathe and clear their air. When high-pressure zones park over heavily populated industrial valleys for weeks, pollution, smoke, and fine dust get trapped near the ground. People living below end up breathing dangerous levels of smog because the wind currents that normally sweep the atmosphere clean have completely vanished. It transforms a simple temperature anomaly into an urgent public health crisis. When weather patterns lock in place for extended periods, entire regional water systems begin to fail under the stress. Reservoirs that provide drinking water and irrigation dry up completely during persistent dry blocks, forcing towns to truck in bottled water. Meanwhile, groundwater aquifers cannot recharge quickly enough during flash flooding events because parched ground simply repels the rapid rush of surface runoff. Have you noticed your local weather getting stuck in long stretches of extreme heat or endless rain lately? Let us know in the comments where you are watching from and what strange weather patterns you have seen, and consider subscribing to stay informed on how our atmosphere is changing. Now, let us turn our attention to an even bigger player in the global weather arena, the tropical Pacific Ocean. Stretching across thousands of miles of open water between South America and Asia, the Pacific Ocean holds more heat than any other body of water on Earth. Every few years, this ocean swings back and forth between 2 powerful states known as El Niño and La Niña. During an El Niño phase, warm water piles up across the central and eastern Pacific, releasing colossal amounts of heat and moisture directly into the sky. This massive burst of energy alters the path of the jet stream, creating heavy winter rains in California and severe droughts in Australia and Indonesia. During a La Niña phase, strong trade winds push that warm water far to the west, allowing cold water to well up from the deep ocean off the coast of Peru. For decades, meteorologists tracked these events like a predictable pendulum. An El Niño would last for a year or two, followed by a neutral period, and then a La Niña would take over before the cycle restarted. Forecasters could look at ocean buoy data and accurately predict global weather trends 6 to 9 months in advance, giving farmers and governments plenty of time to prepare. However, something unprecedented happened between 2020 and 2023 that completely broke the historical rulebook. For the first time in the 21st century, the world experienced a rare triple dip La Niña, where cold conditions in the Pacific persisted for 3 straight years without a break. Then, without a normal transition period, The Pacific violently swung in the opposite direction, producing a powerful El Niño that shattered global sea surface temperature records. When researchers analyzed the heat content of the ocean during this flip, they found numbers that went far off the standard charts. In 2023 and 2024, the North Atlantic and global ocean surfaces remained at record warm levels for over 400 consecutive days. Ocean scientists who had spent their entire careers studying marine temperatures admitted they were witnessing anomalies that traditional computer models simply could not account for. This brings us to a crucial detail that many people overlook when discussing ocean warming. Oceans do not just warm at the very surface where waves splash against boats. Instruments called Argo floats, which drift through the seas and dive down more than 6,000 feet, reveal that ocean heat is penetrating deep into the water column. The amount of extra energy absorbed by the oceans in recent decades is equivalent to several Hiroshima-sized nuclear bombs detonating beneath the waves every single second. This deep layer of thermal energy creates massive marine heat waves that can persist for months or even years. These underwater heat waves decimate coral reefs, force fish populations to migrate thousands of miles toward the poles, and disrupt global fishing industries. Entire coastal communities that rely on marine ecosystems suddenly find their nets empty because the cold water species they depend on have fled into deeper, colder trenches. Marine biologists monitoring the Great Barrier Reef in Australia and kelp forests off the coast of California have documented widespread habitat loss caused by these persistent thermal layers. When kelp forests die off, the entire base of the coastal food web collapses, affecting sea otters, fish nurseries, and commercial fisheries. The oceans are essentially running a sustained fever that shows no signs of breaking. All of that stored ocean heat acts as pure rocket fuel for extreme tropical storms. When a hurricane or typhoon travels over water that is 85 degrees Fahrenheit or warmer, it can undergo rapid intensification. Rapid intensification means a weak tropical storm can explode into a catastrophic Category 5 hurricane in less than 24 hours, giving coastal cities almost no warning time to organize mass evacuations. We saw this exact scenario play out with Hurricane Otis in 2023 off the coast of Acapulco, Mexico. Standard forecast models predicted a mild tropical storm that would bring some rain and gusty winds to the coast. Instead, the storm fed on a deep pocket of superheated coastal water and exploded from a basic tropical storm into a monstrous Category 5 hurricane with winds of 165 miles per hour in just 12 hours. It slammed into the city before emergency sirens could even be fully activated. This rapid intensification is becoming the new normal for coastal communities around the world. In the past, emergency managers had 3 to 5 days to prepare shelters, board up windows, and move millions of residents inland. Today, the ocean is so energetic that a storm can transform into a life-threatening monster overnight, turning routine weather forecasts into sudden high-stakes emergencies.